Yeah, hi everyone. So this is an introduction to PyTorch. It's called the three elements of PyTorch. It's called like that because there are three things that are particularly interesting about PyTorch, and we are going to learn about those. So yeah, what is PyTorch? I will try to introduce PyTorch from three, let's say, fundamental principles. So PyTorch is essentially a tensor library, but it's only one thing that PyTorch is. PyTorch is also an automatic differentiation engine, and of course PyTorch is also a deep learning library. So there are three interesting things about PyTorch that we are going to talk about. So we have a tensor library, an automatic differentiation engine, and we have a deep learning library. So the whole package, that sounds just like TensorFlow, right? So yeah, kind of. It is kind of like TensorFlow, but if you think about it like that, Python is also just a scripting language. Because yeah, we have, let's say, Ruby or Perl. So why do we need Python then, right? Or similarly, you may be using Visual Studio Code, which is a very popular text editor. It's also just a text editor, right? There's also Vim or Emacs. So why PyTorch? There is probably a reason why people like PyTorch. So here's a chart showing the usage trends of popular deep learning frameworks. And here highlighted is PyTorch, and you can see on the left hand side from March 2018 to the right hand side, it should actually go up to 2022. You can see that there is a huge growth in the usage of PyTorch compared to, let's say, other libraries like TensorFlow and Caffe and so forth. And there is probably a good reason why people use PyTorch. So as a former TensorFlow user, personally I use TensorFlow around 2015. Why do I like PyTorch, you might wonder? So why did I switch to PyTorch at some point? So I will tell you more about that after I gave you the introduction to PyTorch. So for now, maybe stay tuned and I will come back to this question. So coming back though to the more general question, what is PyTorch? And we will now tackle these three things one step at a time. So we talked about PyTorch being a tensor library. Yeah, so what is a tensor? A tensor is essentially a mathematical object that we can then, let's say, manipulate with linear algebra. However, in a computer context, it's more about, let's say, being a data structure for different data types that we can then also use in the context of linear algebra operations. So there is the concept of a rank 0 tensor, which is essentially just a scalar, just a single number. So here I'm showing you an example of how we can initialize a rank 0 tensor in PyTorch. So then there's also the concept of a vector, which is essentially a rank 1 tensor. So here I'm initializing a so-called rank 1 tensor, and I use the same torch.tensor function here. And then there's also the concept of a rank 2 tensor, which is essentially a matrix. So for the matrix, you can think of it as multiple vectors concatenated together. So here I have a 2x3 matrix. We can continue playing this game if we think about, let's say, a color image. A color image really is a stack of multiple matrices here. So especially if we think about RGB color image where we have three color channels, red, green, and blue. And then, so this would be essentially a 3D tensor, a rank 3 tensor. So as you can see, it's essentially a stack of multiple matrices. And at the bottom, I'm showing you how to stack two matrices together. So this would be a 2x2x3 tensor. And then taking this up another dimension, we can also then stack multiple color images. So here, that's a stack of multiple color images. And as you might guess, this would be then a 4-dimensional tensor or a rank 4 tensor. And on the right-hand side, I'm just stacking two 3D tensors, A and A, which we defined previously. So I was going through this pretty quickly because this is not particularly interesting. I just wanted to highlight the aspect what a tensor library is. So as you may have noticed now, what I showed you, this tensor library looks pretty much like an array library, which you may have already seen, right? So if you have used NumPy before, this torch.tensor might look very, very similar to NumPy array, which you may be familiar with already. And this is actually by design. This is intentionally so that it is easier to use. But so you may wonder, okay, if we already have numpy.array, why do we care about, let's say, reinventing the wheel and using something like Torch Tensor? So the reason is that Torch Tensor adds GPU support. So what is very easy is if you have a tensor, you can just move it to a GPU. Here I'm showing you one way to do that. So here I have, let's say, a GPU that supports CUDA, which is a specific software library for GPUs by NVIDIA. And let's say I have multiple GPUs, 0, 1, 2, 3. So there's like an index number for the GPUs. I can also specify to which GPU I move it to. So 0 would be the first GPU in my computer if I have multiple ones. Then on top of it, there's also something called autodiff support or automatic differentiation support. So what is that? Let's talk about this next. This is where it gets a little bit more interesting, I would say. So automatic differentiation is a concept for, let's say, doing the heavy lifting, the mathematical stuff for us automatically. So the term automatic implies there's something automatically happening, and that's differentiation, which is a mathematical concept for computing derivatives and gradients of computations or functions. So assume you have a model like that. So here I'm showing you an abstract, let's say, drawing of a logistic regression model where we have only one input on the left-hand side, x1, that is one feature input. Then we have only one model weight corresponding to this feature input, and then B is the bias unit, and they get combined by, let's say, computing a weighted sum, and then the weighted sum goes through a logistic sigmoid function, and the output would be then a class membership probability. So this is a very abstract, let's say, drawing of how a logistic regression model looks like. In practice, when it comes to, let's say, the mathematical details, it's always helpful, at least for me, to draw something called a computation graph. Yeah, here's how the computation graph would look like. Going through it step by step, so we have on the left-hand side x1, which is a feature input. We have w1, which is a model weight, and we have b, which is the bias unit. So first we multiply x1 with w1, and we save the result in a temporary variable which we call u. Then we take u and add the bias to it here. And we save the result of u plus b, as a temporary variable v. And then lastly, we apply this sigmoidal function here to v and get the output a. Yes, so because I was running out of space when I was making this figure, I didn't write out explicitly what this function sigma is. So here at the bottom is a definition of this function. It's the so-called logistic sigmoid function. But yeah, in this talk, it doesn't really matter that much because we are not here to talk about logistic regression, but to introduce some of the interesting things about PyTorch. So in a real-world context, we are usually interested in computing the loss derivative with respect to the weights so that we can update the weights. Here, the loss function didn't quite fit on the slides. So what we are going to do here is we are only computing a part of it. And a part of it is computing the derivative of the output A with respect to one of the model weights W1 here. So we are computing the derivative of A with respect to W1. So how would we do that, let's say, if we don't have any computational tool that can help us with that? So what we can do is we can apply the chain rule and compute these individual derivatives and then combine them together. So if we don't have any computational tool that helps us with that, what we would have to do is we would have to compute the derivative of A with respect to V, then the derivative of V with respect to U, and then the derivative of u with respect to w1. And then we can combine them all and compute in that manner the derivative of dA with respect to w1. And if we want to do this very concretely, in this case, the individual derivatives are as follows. So we don't need to, let's say, go through the details how they were derived, but let's just assume I did all the tedious math for you, and we have the following derivatives for these individual 3 steps. Now let's add some numbers to the game and see what some actual values would be. So let's assume for the input for the forward pass we have 0.1 for the bias unit, 0.2 for x1, the feature input, 0.3 for the weights. Then at this point u would be 0.06, v would be 0.16, and the output, if we put that through the sigmoidal function, what we get is 0.5399. So, and then when I put this through the derivative, what I get is 0.0497. However, this is very tedious. This is really not fun because we have to derive everything by hand and it's very error prone. And this is not really something we would want to do if we, let's say, work with bigger computation graphs, for example, when we implement bigger neural networks. And yeah, this is really, I would say, a horror story doing that for a whole neural network. So how can PyTorch now help us with that? So in PyTorch, of course, we can code this all up. So here I'm showing you the forward pass in PyTorch. The result here is exactly the same that I got when I computed things by hand, which is good. So you can see we can use PyTorch just like as a calculator, like we can use NumPy. And then when we compute the derivative, I can also just code up the individual derivatives and put them together. But again, this is really still very tedious. I didn't really solve the issue of making this easier when we work with bigger neural networks. So there is something really cool in PyTorch, and this is called autograd or automatic differentiation. And there's a way we can do all of that automatically without having us to derive anything by hand. So how do we do that? So for that, we just have to define our computation. Let's say we have to just run our model, and this is here on the left-hand side where we run the model in the forward pass. This is really how we run the model from left to right to get the outputs, and that's something we usually do when we encounter new training examples or even if we apply our model on, let's say, new data. So this is just the regular forward pass. So for training or for applying this concept of autograd, what we do is we say that at least one of the variables requires a gradient. So here in this case we are interested in the gradient of W1. So what we can say is requires gradient equals true. And then when we run this computation, what will happen is that PyTorch will construct a computation graph in the background, and once this computation graph exists, it can then go backwards and compute all these gradients automatically. And you can see on the right hand side, this is very simple. So computing the gradients here, or the derivative, is really just one line of code. We import the gradient function here from autograd, and then we just call it. We just say compute the gradient of A with respect to W1 here, right? So, and this is it, and it gets us exactly the same result that we got before. I mean, this is a simple computation graph, so it's maybe not super impressive, but think about doing that for, let's say, a bigger neural network. If we would do it by hand, if we have a neural network with, let's say, 20 layers and different activation functions, this would be very, very, very painful. And something like autograd can make our life here way easier. However, if we work also with big neural networks, it would be very tedious if we would have to call this grad function every time on each individual weight. So PyTorch, in essence, is also a deep learning library, and it makes these things incredibly easy. So we don't have to even manually call the grad function. It is doing it for us behind the scenes. So the reason I showed you this grad function really is to give you a taste of what PyTorch is doing behind the scenes, to kind of like understand it a little bit better. So now we are getting to the more, let's say, even more interesting part. We are going to talk about how PyTorch helps us concretely with implementing deep neural networks. So in particular, I'm going to show you how PyTorch works in 3 steps. So here I have the 3 steps: defining the dataset, defining the model, and then defining the training loop. And that is how I would set up my, let's say, Jupyter notebook or code script that I would write in my code editor in this particular order. And I will actually show you also a hands-on example later. However, I think defining these things in that order is quite boring because you are probably very interested in learning about the model first and then the training loop. And the dataset doesn't really matter, I think, for a demonstration of how PyTorch works, because it should work technically with any type of dataset. So I think the dataset, we can put that last. So in order to, let's say, teach you how PyTorch works, let's reconsider our order here. Let me talk about the model first, then I will show you the training loop, and then lastly I will show you how we set up the dataset. So step one is defining the model. So here we are going to implement a convolutional neural network, which we call PyTorch CNN. So most of it looks just like a Python class. There is only one little thing what we do here, and that is using the parent class torch.nn.module. So, and this is really it. The rest looks really like just regular Python class code where we have the constructor method. And here in this constructor method, we call super, which is just inheriting things from the parent class. That's just a regular Python concept. And then here we set up our layers. So we here have two convolutional layers, one layer, another convolutional layer, and then we have a linear layer as the output layer. So I should say in the constructor class, usually what people do is they put everything in there that has a state. So each convolutional layer will have model weights and bias units, and the same is true for the linear layer. So there will be model weights that we want to learn because that's part of the neural network training. So then we define the forward method. So here I'm just keeping the same code as before. Now the interesting part is the forward method. And here in the forward method, we really put all the things in the right order, how we want them executed. So here, assume x is a new data point that we receive at that point. And then we have like the series of computations. What we do first is we call the first convolutional layer. Then we call a ReLU activation function. Then we call a max pooling layer. Then here comes our second convolutional layer, another ReLU activation function, and then again another max pooling layer. And then the output, because it will have channels from a convolutional operation, which is quite, let's say, incompatible with a fully connected or linear layer, what we do is we flatten this so that this will be just the number of training examples times the number of dimensions. It will be a matrix at this point, which we then can fit or feed to the linear layer in the end, which will then output our logits. So the logits are the outputs of the last layer. So there's one thing worth highlighting. Here I intentionally used the so-called functional API. So the functional API is something that we can use if things don't require a state. So something like the ReLU or max pooling functions, they don't require a state. There are no weights that we need to learn. So in this case, we can use the functional API. We can't use the functional API for something like the convolutional layers or the linear layers because they have the weights and biases. But for something like activation functions or other operations that don't have a state, we could technically use the functional API. So after we defined the class, we can then initialize it as follows. So usually I like to set a random seed manually. So because each time we usually initialize a neural network, it will have random weights to start with. And just to make it more consistent, if someone executes the same code and wants to get the same results, it's sometimes useful to just manually seed the computing environment so that the same starting weights are used each time. I just see this is a little typo here. It says convet. It should have been PyTorch CNN, of course. So you are initializing here your PyTorch CNN. And then this is an optional step where you can transfer your model to a GPU, but this is not required. This is an optional step. If you have a small model, you could technically train it on a CPU. However, I would usually not recommend it when it comes to convolutional networks. If you have a network that is just linear layers, it might work, it might run reasonably fine. But as soon as you introduce convolutional layers, it can get very expensive. And if you run something, especially on a laptop, they can get quite hot. And I don't think that's recommended or good for the computer. But yeah, getting to the next topic. So I showed you now how we, let's say, set up the PyTorch class. This is one way we can set it up. I showed it maybe in the most simple way in terms of introducing concepts. However, in practice, what I like to use is something called sequential. And it can really make our life easier because then we don't have to memorize in which order everything goes. So if I go step back, so here, when we look at this again, I defined my convolutional layers, and then I have to memorize in which order I use them here. So I have conv1 and conv2, and sometimes I think this can be very error prone because you may mix things up accidentally, especially if you have a lot of layers. If you have, let's say, 30 or 40 layers, it's quite tedious to rewrite them here at the bottom. So this is something I think it's fine for a small network where you can look at this in a few lines of code and make sure everything looks okay. But I personally find it more convenient to work with the so-called sequential API. So here I'm showing you how that works. So the difference here is in the sequential API that we put everything in this sequential class context. So here it's the same network. We are essentially just listing out these things here. So notice we have still our conv2d here. Then now, instead of using the functional API though, we have to use the object-oriented API. So we are putting here an n.relu. Technically, this is overkill because something like an activation function doesn't have a state, but this is just to make it compatible with sequential. And then we also put the max pooling here, the second convolutional layer, relu, and again max pooling. And also, I mean, this is not required. We could also put flatten and linear up there. But what I like to do usually is to separate the feature extraction and the output layers, the classification layers, the linear layers. So here what I have is, I call this just this attribute, I call it features, which kind of like reminds ourselves that deep neural networks are essentially doing implicit feature extraction. And then we have the classification part down here. Again, I'm using sequential here, and I'm putting now the flatten again here, and then the linear layer, the output layer. And the difference here now is that I don't have to, let's say, call all of these layers individually like I did before. So going a step back, before I had to, in forward, remember the order and call them, let's say, one by one. Now, if I go forward again, what's more convenient is I define the order up here, and then I can just call these. I can say dot features and then classifier, and that's it. I don't have to memorize in which order I put these things. Personally, I think this is way less error prone than the other approach. Yeah, here just to highlight it again, so we have two sequential parts. So one, I set it up that I have the features, the convolutional layers up here, the feature extractor part. And then the second part here is the classification part where we have then the linear layers. It could be also, of course, multiple linear layers. But of course, you can also combine this into one sequential part. You don't have to separate it like here, like I did. Okay, so now that we have the model, let's get to the interesting part, defining the training loop. So again, just for reference, let's initialize the model and the optimizer again. So here we have the model, which we initialize here. Then we optionally put the model, let's say, on a different device, like the GPU. And by the way, I will also show you a hands-on coding demo after that. So I'm going through the slides here to kind of like highlight the concepts, but I will also show you all the code in context later. And then also we want to set up an optimizer. This is how we, let's say, update the weights essentially. So it's essentially when we do gradient descent, we can consider a standard stochastic gradient descent update, or we can use something fancier like stochastic gradient descent with momentum. My favorite go-to to start with is the Adam optimizer because it's very robust in terms of choosing a learning rate. It doesn't require as much tuning to work well. And so the optimizer, what it really does, it's the one that takes care of updating the weight parameters. So once we, let's say, do the backpropagation, the weights will then be processed by the optimizer to update the model weights. So the optimizer needs to know what the model weights are in order to update them. So here we, as input, provide model.parameters, which will list all the model weights and bias units of our model here, so that the optimizer can then update them. So here we are just telling the optimizer what the model parameters are, and then we will see later in the training loop how they are actually updated. Yes, so one of the essential parts of the training loop is to iterate over the training set. So what we have here are two for loops. One for loop is iterating over the epochs, and the second for loop is iterating over the individual training examples. And we have something like a training data loader or train loader. And we will define that after we talked about the training loop. So this is part of the dataset. We will define that next. So what we do here, notice, is also we put the features, let's say images, and then the targets, which are our labels, we put them also on the same device that we put our model onto. And this is because we have to make sure that things are on the same device. If we have our model on the CPU, we can also keep the features and targets on the CPU. But if we use a GPU, it makes sense to also have the data on the same GPU that our model is. So next, the next part is computing the predictions, and also here calculating the loss. So here we have the forward pass where we compute just the predictions, the logits, and then we feed the logits into the cross-entropy loss. So one thing really worth highlighting and emphasizing is that the cross-entropy takes care of the softmax or log softmax internally, which means that we really have to be careful to feed it the logits and not probability scores. So we don't want to have the softmax layer as our output layer. We really want to just have the unscaled values from the network that go into the cross entropy, because it already takes care of the softmax for us. And similarly, we also want to make sure that the targets are integers, like in tensor of integers, like 1, 2, 3, if we have, let's say, 3 class labels, or just to make it more clear, these should be integers, and it will already take care of the one-hot encoding for us internally. We don't have to worry about one-hot encoding class labels if we have a multi-class prediction problem here. Now assume we have computed the logits and the loss. Now the core of the learning is really computing the backward pass, that's the backpropagation. So there's one step we do, which is zero grad. I will tell you in a moment why it's important. And then backward is really where we compute the gradients, where we previously used the grad function, if you remember. This is what backward is doing, using loss as the output. It's essentially similar to calling grad on loss with respect to, let's say, one of the weights, W1, but it would be doing it for all the weights, which is very convenient. And just to hone in on this zero grad, so this is also very important, because if you don't do this, if you forget zero grad, what will be happening is that the gradients will be accumulated across multiple iterations. And this is usually something we do not want. We don't want to accumulate gradients. There are some specific, let's say, research contexts where we want to do this, but normally if we just want to train a network regularly, we don't want to accumulate gradients. So it's important to always set the zero grad here before we call backward and then the step. So the last step here is then updating the model parameters. So here in this last step, the optimizer that we initialized previously here, it will take a look at the gradients computed from backward, and then we'll update the model weights. And then lastly and optionally, and this is a very abbreviated version, what I like to do is I usually also like to keep track of the model performance. Usually the training accuracy and the validation set accuracy, so I can see how well our model performs. I usually also plot the loss function, but I'm really particularly interested in seeing the training accuracy and most importantly the validation accuracy, because that gives me, let's say, the information about how accurate my classifier is, how well it's training. So I will actually in a demo show you a little bit more, but so this would be, I would say, the minimum that we want to look at. And we will also see in the code example how this compute accuracy function is set up. But yeah, just to finish up with step 3. So the last part here is defining the dataset. I was actually thinking really hard what dataset to use. I had different ones I played around with, spent a lot of time finding an interesting one. I settled on cats and dogs, but then I thought, well, we only have so much time here in this talk, so let me not, let's say, go fancy, and let's just use something that is relatively simple so that we can focus, let's say, more on the code rather than the dataset. So here we are using MNIST, the hello world of deep learning. It's probably not very interesting, but I think it's just simple enough so that we can focus more on the code. And also there is actually a built-in version in PyTorch. So MNIST is already available in PyTorch, but to make it at least a little bit interesting, we are using a version that comes as PNG files. So if you download this, it would be two folders. So there would be a test folder and a trained folder with the corresponding images. And each folder has 10 subfolders where the folder name denotes the class label. So I was choosing it like that, so then you can use the same code for any new data set. So if you have a data set and you just structure it like that, where you have a test and a training folder and you have an arbitrary number of subfolders for each, you can use the same code we are using here and apply it on any new image data set. So we are using a few convenience functions. So one is from Torch. It's a random split, but the more interesting one here is the one from Torch Vision. So Torch Vision is a library, I would say, affiliated with Torch, and this implements utility functions for specifically vision tasks. So if you work with image data, this is something that implements some functions that make our life easier. One of them is image folder, and then with image folder we can actually create a PyTorch dataset very easily from, let's say, the training subfolder that I have just shown you. And then we can do the same thing for the test subfolder. And one more thing here is that we are defining something like a transform here. And this is some custom data transformation. I will show you in a second how that looks like. But before I do that, one more thing is here the random split function. So with a random split function, we are creating ourselves a validation set, because what I showed you before doesn't have a validation set. It was just training and test sets. So what we are doing here is we are splitting the 60,000 examples. So MNIST has 60,000 training examples. We are splitting them into 55,000 new training examples and 5,000 validation set examples. So now we have a training set, a validation data set, and a test data set. Let's look at this transform that I just introduced. So for this transform, we can really be creative and do whatever we want. And this is pretty much pre-processed already, so we don't have to do much there. But just to illustrate some points that we could technically do, I'm playing around with some of the transformations in Torch Vision here. So what I'm doing here is I'm first resizing the image to 32 pixels height and 32 pixels width. And then I'm doing something like a random crop. So a random crop will randomly pick an area 28 by 28 pixels large and wide from this 32 pixel 32 by 32 pixel images. So this will be randomly different each time, and you can think of this as a way of doing data augmentation. So we are kind of like creating like these slightly different crops every time the data point is sampled, and this can sometimes help the network with, let's say, reducing the effect of overfitting. An important part of this pipeline here is toTensor. So this toTensor will convert whatever the format the image is in, and I think it's in a format by the Python imaging library, it will convert this into a PyTorch tensor. And in the process of converting it, it will scale also the images or the pixels of the images to be each in the range between 0 and 1. So that's also important to keep in mind. Some, let's say, some neural networks train better if you have them also with negative values centered at 0. So what I'm doing here is I'm converting them to -1, 1 range. There's this normalize function, which is essentially a standardization. But so just to highlight it here, each value stands for a channel. The way we loaded the images, they are actually having 3 channels, although they are grayscale images. But this is the way you would do this, let's say, with any color image you are working with. And each value here stands for the mean. So there's a mean for each color channel, and then there's also a value for each standard deviation. So there are 3 standard deviations and 3 means for standardization. So standardization works like this, where we have some pixel value, and we subtract the mean, and we divide by the standard deviation. So if we have something like a value like 0, we subtract 0.5, and we divide by 0.5. Oops. This should be -1, correct? And similarly, if we have a pixel value of 1, we subtract 0.5, and we divide by 0.5, the result should be 1. So what will happen is that after applying this normalization, the images will be in the range between -1 and 1. And then we can do also the same thing for the test set. So here I set up the test set transformation a little bit differently, because during inference or testing time, we don't want any randomness, because then that would mean every time we compute the accuracy on the test set, the results might be slightly different. We don't want that. So what we do is here we replace the random crop by a center crop. So it will always take the 28 by 28 center image. Yeah, let's now look at the data loader. So what we have here is the training set as input. That's the main, let's say the main argument for the training loader. Then we can also define the batch size. And then there's something called drop last equals true. So this is not a requirement, but sometimes when we work with data sets, the total number of examples is not evenly divisible by the batch size. And then sometimes it can happen that, let's say, the last batch is relatively small. Let's say the batch size is 64 or 128, and the last batch has only 3 or 4 images. And this can sometimes throw off the training, because, yeah, this is a mini batch gradient descent that is then very accurate, because we only consider 3 or 4 examples in the batch. So personally, I recommend dropping the last batch. It can sometimes help with, let's say, smoother training, but it's, again, not a requirement. In many cases, the network just trains fine if you set that to false. A relatively important parameter for performance is the number of workers. So what happens is that the data loader will load the next batch on the CPU. So if you don't specify multiple workers, which corresponds to multiple parallel processes, you can accidentally create a bottleneck, so that the training will slow down because the GPU is waiting for the next data batch. By specifying a number of workers that is more than, let's say, 1, it will pre-process data sets or the next mini batches and have them ready for the GPU when the GPU requires it. It's essentially using multiple CPUs on your computer to avoid creating bottlenecks through data loading. And then lastly, shuffling. So that's also, yeah, of course, important to prevent cycles during training. Next, the validation loader. So it looks very similar, so we don't have to go through everything here again. But here, of course, we don't need to drop last, because here it's not, let's say, training. Here we are just evaluating. So here I would recommend setting this to false, so that all the data points in the dataset are considered. And then we also don't need to shuffle. I mean, you can shuffle, but it won't affect the accuracy, so it doesn't really matter. So it's maybe overkill to shuffle here. And then the test loader. Again, the test loader is similar to the validation set loader, so nothing really interesting to discuss. Wow, that is a big question. Why do I like PyTorch? Yeah, getting back to the earlier question, why do I like PyTorch? I mean, it's maybe you have already seen that. It looks very pleasant, right? It's relatively easy to work with. So the reason why I like PyTorch is really that it is, let's say, very Pythonic. It's what people call Python code that looks, let's say, very pleasing to the eye. And at the same time, it's also very flexible. So it allows me to, let's say, do custom things in my research. So it's a very powerful framework. A lot of people use it, which is also useful because then you can find a lot of code examples online and lots of explanations online. But on the other hand, what's also nice is that it's very flexible. So when I, let's say, work on a research project, I can tailor it to my needs without, let's say, getting it too much into the way. So for example, in a research project, I once needed to create a custom layer, and it looks a bit complicated, but let's say this is my custom layer, how I would implement it. And the same layer was taken by someone else who created a Keras, a TensorFlow Keras port of that to use it in TensorFlow Keras. And the code was essentially this. And you can see, well, this is so much more work. And I'm not sure if I would be ready for it if I work actively on a research project and I want to just make a few tweaks. This would be, of course, not impossible, but it would be quite a lot of more work. So in that case, what I like about PyTorch really is that it is relatively pleasant and simple to use while being very flexible also for research. Okay, let's get now to a live demo where I show you all the code snippets that I showed you previously in context in an example that we can actually run. But maybe before I get to that, just a little shameless plug here. Also, if you are more interested, let's say, in some more details about PyTorch and also some more advanced, let's say, neural network concepts, let's say graph neural networks or transformers. Yeah, I also have a new book that recently came out this year where I and my co-authors cover a little bit more about, let's say, how PyTorch works and also implement some more neural networks. And also, if you're interested, we have the very first Lightning Developer Conference coming up in June, on June 16th in New York City. So if you're interested in attending, you can go to this website, and there may be still some spots at the time when you're seeing that. So if you're interested, join us at the Developer Conference where we have something very exciting to talk about and present related, let's say, to PyTorch Lightning. And stay tuned for that. So if you're interested, also check that out. But now, like I said, let's get to the code demo. All right, let me now show you how all these things come together in one code file so that we can actually train our network. So I will keep it relatively short because the preamble, the slides was already pretty long. So I will be using a Jupyter notebook with one GPU in the cloud, just so that the training will go faster then compared to, let's say, training it on the CPU on my computer or laptop. So here I'm just starting my Jupyter notebook. And first we will start with some imports, like some basic packages we will need later, NumPy, Torch. And what I also like to do is when we are using a GPU to make the code deterministic, so if other people run this, that they should get the same results. So let's do that. Then the next, some basic settings. So here I'm saying that if a GPU is available, it should use that, otherwise the CPU. And in this way, this same notebook will also work on your computer if you don't have a GPU. Some basic settings, a random seed for data shuffling and weight initialization, a learning rate, the number of epochs to train, the batch size, and the number of classes. Because we are using MNIST, there will be 10 classes. So then the dataset itself. So we will be using a PNG version of MNIST. So we will clone this directly from GitHub. I recommend, if you don't have that yet, installing GitPython so that you can do everything directly in Python here, so you don't have to switch over to the command line. So then here what we're doing is we are importing Git from repo, and it will clone this repository if it does not already exist. So it's a repository I made with the MNIST images as PNG files. Then our data transformation code. Luckily I don't have to explain this again because we already covered this in the slides, but this is again our data transformation code. Then next what we have is our data loaders. So we are setting up now the data sets and then the data loaders from that. So this is the image folder that we covered before. So here we are setting this part up, and then we will get to the data loader here. So we have now the data loader that uses the data sets we just defined. Again, I'm going through this very quickly because we already talked about it. There is an issue. So I should actually make sure that I execute everything, otherwise certain things won't be defined. Also, I find it often helpful to take a look at the images that we are working with. So here, this is just an utility function from Torch Vision that makes a nice little panel here so that we can actually take a look at some of the images, how they look like. So here that looks reasonable to me. So this is a panel of 1, 2, 3, 4, 5, 6, 7, 8 images that we created here. So 8 by 8 is 64. That makes sense. Okay, so next, then the interesting part is our model. So here we are setting up the model that we defined earlier. So we have our PyTorch CNN here. And yeah, this is just our model that we defined earlier. Nothing special. We are using here sequential because that's the most convenient way. The only thing that is different here compared to the slides is that I have now all the channel dimensions filled out. Notice that because the way I created the PNGs, they are actually RGB files. So they have 3 channels. So in that case, you can use exactly the same code on new images, except maybe the height and width has to be adjusted. But normally MNIST would be a grayscale image. It just happens that in this case, these are 3 duplicated color channels. Okay, let's do this. So next, the interesting part is now training. We have defined everything, and now we get to the training. There was this one accuracy function in the slides that I briefly glanced over. So because we have a few more, I would say, minutes, let me just briefly explain the accuracy function. So this is essentially a function that iteratively loads the data from a data loader that we can specify. It can be the training, validation, or test loader. Then it puts the data onto the same device as the model. Then we run the forward pass, get the labels, and we sum up the number of examples we encounter. That's just the number of total data points, just to have it conveniently here. And we also sum up the number of correct predictions here. And in the end, then we compute the accuracy as the number of correct predictions divided by the number of examples. So this is just one iterative way of computing the accuracy. And this is based on the assumption that the data set is too large to load it into memory, which is why we do it incrementally by fetching batches from the data loader. In practice, so this is a function I defined myself just to illustrate the main concept. In practice, I also highly recommend a package called Torch Metrics, which is a more elegant version of that, which implements a couple of different metrics in this similar fashion. So I highly recommend checking that out. So, but we want to keep things simple here. So we are just coding it, let's say, from the ground up, instead of introducing more things. And then finally, the training pass, so the training loop that we saw in the code, in the slides, we defined the optimizer. And I have just added some sugar here to do a, let's say, timing, so we can see how long the training takes. But the rest is really the same, where we iterate over the epochs. I should say there's one more thing I haven't talked about. It's this no gret. And this is kind of important in terms of evaluation. So I mentioned before, so if we look at this whole training loop here again, that we have this backward pass. And with this backward pass, it will destroy the computation graph in each iteration. So when we call this here model, it will execute the forward pass of the model, and it will build a computation graph in the background. Then if we call backward, it will, let's say, destroy this computation graph, so that in the next round, it will create it from scratch again, and it will destroy it again. And this makes PyTorch a dynamic framework, so you could technically make changes in each iteration. you can maybe swap out the loss function sometimes, and each time you will get a different computation graph, which can be convenient in certain contexts where you do certain types of experiments. But then you have to be careful. If you don't call backward, it will make the computation graph larger and larger and larger because it doesn't destroy the computation graph. If we just compute the accuracy, we don't need any backpropagation. We don't need a computation graph. However, we call also model here multiple times, and this will cause the computation graph to become bigger, 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 and bigger. And if we have a large data set, this might even crash your notebook here. So in this case, a good habit is to insert this width context, and under this width context, everything that comes under here won't have a computation graph. Because again, we don't need the computation graph here. We only need the computation graph during training for calling backward. So in this case, to make it more memory efficient, we use this torch no-grad context. Except that everything you see here should be the same thing you have already seen on the slides, except that I, let's say, extended the logging a little bit so that we have some information about the loss function here. It's just printing out the batch every 100 batches, it just prints the loss. And then after each epoch, we compute the training accuracy and the validation accuracy and also plot that. Notice there's one little detail here. It's a model eval, and we have here a model train. So in this case, it doesn't really make any difference, or it doesn't matter whether we use it or not. But in practice, where you have methods like dropout, where you have a different, let's say, training and inference behavior, it's best practice to insert train and eval, because during training, dropout will drop random nodes, but you don't want it to drop random nodes during evaluation. So if you do that, it will take care of dropout not dropping these random nodes. So personally, I just add them always. I have train and eval, so just to make sure you never forget that. So if you, in case you have a network with dropout, you are kind of like taking care of this already. And then in the end, we are just seeing the runtime, how long it takes to run. So let me just run this, and then maybe it doesn't take too long. We can maybe even see some of the outputs. So it's probably running here. I will just wait here with you. And it should, every 100 batches, it should print the loss. And we want the loss to go down. So this is something we want to see. We want to see it goes smaller. It doesn't always happen, see, because it's stochastic gradient descent. There is sometimes a little bit of noise. So it's not always strictly monotonically going down. But overall, we should see a trend that it goes down over time. So there's one more thing we should add. So we are currently computing the training accuracy and the validation accuracy. One thing we are not doing here is the test accuracy. So let's also add that. Same concept. We are using the model, the test loader, and then to compute the test accuracy. Notice that I didn't really tune this network, but it's performing very well. So you can see training accuracy 95%, validation accuracy 95%. There is no overfitting in this case. Also, the training accuracy is actually higher than the validation set accuracy. It doesn't mean anything. It's just such a small number, but it basically means they are identical. So in that case, there is no overfitting. We can see it's slightly overfitting, but not too bad. And I think we can attribute this fact that there is such a small degree of overfitting also partly maybe to our data augmentation. We kind of have, remember this data augmentation where we have like this random crop. But yeah, please feel free to experiment. Your mileage may differ. So things you can try is really, I think it shouldn't make such a big difference, but you can try with and without this normalization. Personally, sometimes it helps, but not always. In practice, you may want to maybe play around with that. You can also resize this. So you can maybe replace this by center crop, but what you can also do is you can just leave the original size. You can just change this as follows. This should work. Actually, a minimum example should be like this, where you only have the two tensor. That should also work. You can compare the performance to that. You can tune the learning rate. So you can tune the batch size, 64, 256. There are so many different things you can try to see whether the performance, let's say, gets better or worse. Of course, you can also change things here. You can add more channels. You can maybe double the channels. You can maybe half the channels. Maybe you can see whether you can do without one of the convolutional layers. You can maybe also remove one of the linear layers here. I just noticed my code example here has one more linear layer than the one I had in the slides. So that might be another thing to experiment with. So to be precise, I would take out these two here and see if that makes a difference. And that is just an overview of the different hyperparameters we can play with so that we can bridge the time until the training here completed. We are already at epoch 9, so we're getting close. Let's take a look. It actually looks like it's converging. So we see approximately equal performance. In every case we can see training and validation accuracy are almost equal, which is always a good sign that there is very small overfitting. It has not quite finished. It runs in 3.49 minutes. Actually, I'm using a very slow GPU, a very cheap GPU, because I didn't want to spend too many cloud credits on playing around with things here. But you can see even on a cheap GPU, I think it's 50 cents per hour, it can already train very fast. And then the total training time was 3.84 minutes. And the test accuracy is 99.18. And I don't think you can actually do much better than that, because there are actually some labeling errors in MNIST. So MNIST is not perfectly labeled, so 99% is maybe as good as you can get. If you get something like 100%, that should make you a little bit suspicious. So there was like this one article, I shared that on Twitter, where someone had a 100% accuracy on MNIST and also other data sets, and I looked a little bit into this code, and there were some issues with that code. So actually, if you even just randomize the labels in the data set and the test set, you still get 100% accuracy, which is something that should not happen in practice. So 99.18% is probably as good as it can get. If you want to play around with that, I think what's more interesting is how much smaller can you make the network and still get that that performance. Like, how many layers can you remove? How many parameters can you remove? Can you make a simpler model that achieves the same performance? But with that, I hope you liked this little introduction to PyTorch.